Good morning, good afternoon, wherever you may be in your day. As always, thank you for choosing to make chemistry part of that day. Once again, look at our objectives. We're building vocabulary in Chapter 1. Each set, there's kind of matching sets of definitions, and we'll go board by board. This may be intuitive, but macroscopic versus the microscopic nature. And this comes up over and over again in chemistry, because what we measure and we talk about are macroscopic observations, but we never see an electron, an atom, a molecule, an intermolecular force. We can't see that with the naked eye, so we're trying to extrapolate what happens in the microscopic world to explain the macroscopic world that we live in. Okay, so what do I mean by that? Macroscopic is simply something you can observe, whether that's something you can see, touch, feel, measure, those types of ideas, where microscopic is something so small you can't actually see it. I think you know exactly what I'm talking about, so I'll keep this short. You know, when you look at a cloud, the cloud is macroscopic. You can see it. You don't need any fancy equipment. But what's a cloud made out of? Little droplets of water. And what are little droplets of, and even a droplet of water is macroscopic. But what's inside a droplet of water? Well, we have little water molecules, which most of you know is H2O. 2 hydrogen atoms and 1 oxygen atoms. So a lot of times in the chemistry books, we'll represent this microscopically, or macroscopic and microscopic, showing you what we observe and what's it really made out of. So you have different colors represent the different elements, and each shape, sphere, ball represents a different atom. So this would be 1 red oxygen atom and 2 blue hydrogen atoms, and you put those together. All right, a little bit more important and maybe needing a little bit more explanation is physical versus chemical. And this gets used two ways. There's chemical and physical properties, and there's chemical and physical changes. And they're very related to each other. Easiest way to think about this. If what you have at the beginning is the same as what you have at the end, substance-wise, chemical-wise, it's a physical change. If you create something new, or you destroy, decompose, burn something, it's a chemical change. Okay, so what are some examples of this? So, physical changes. Again, you have the same thing at the beginning and the end. So we're talking about a change. This is usually a phase change. You melt something, you boil something, you freeze something, you evaporate something, you condense something, you sublime, deposition, those types of ideas. So you're talking about a phase change. The other place you'll see this is actually, really a physical change. You grind something. You grind your coffee beans. You take an axe to a piece of wood. You still have an axe, you still have wood, but the shape of the wood changed. Mortar and pestle, those kinds of ideas. Grinding, smashing. A little bit more subtle and sometimes throws people dissolving things. If I take salt and water and I mix them together, the salt magically disappears. As you guys know, it dissolves. And it's still there. You still have salt, you still have water. They're still there. They're just mixed together. Same thing with the Wicked Witch of the West. Water gets thrown at her at the end. She dissolves in the water, does not melt, dissolves in the water, and you have witch and your water, and conceivably you could separate that back out and recreate the witch. Okay. If you're measuring something and you still have it at the end, so if I step on the scale and get my, I don't know what I weigh, 180 pounds, and I step off the scale, I still exist. That was a physical measurement. That was a physical change, a physical property, my mass. You didn't have to destroy me to get my mass. You don't have to destroy me to get my volume. So those types of ideas. Density, most of our measurements we make do not destroy the sample we're measuring. Those would all be physical measurements, physical properties, physical data. If you actually destroy it in the process of doing it, so the energy of combustion, you burn something, it doesn't exist anymore. You turn it into carbon dioxide and water. So that would be a chemical change or chemical property. The fact that iron reacts with oxygen, or iron, when exposed to oxygen, rusts, that's a chemical property. The iron's not there anymore. It's become rust. It's become iron oxide. Gasoline is flammable. Well, when it bursts into flame, it's not gasoline anymore. Chemical change. We get something new coming out of that. Rusting, burning, decomposing, rotting, those are kind of buzzwords you'll hear for chemical changes. Getting trickier still. Intensive versus extensive properties. So here's how I remember it. Intensive, it's identity, match the eyes. Extensive, it extends with the amount you have. That's how I remember it personally. So what does that mean? Intensive property, if you have a drop of something or the entire ocean of something, it's going to have that same property. So water has a density of 1 gram per milliliter, whether I have a little itty-bitty drop of water or the entire Atlantic Ocean. Now, the mass of the ocean is very different than the mass of a drop of water. So that would be an extensive property. The amount matters, it extends. So mass, volume, the amount of heat something holds, those are all extensive properties. Temperature is a measure of average kinetic energy, and that's going to be the same whether you have a small sample or a large sample. The temperature is regardless of size. So temperature and heat sometimes throw people, so I want to put those up. Temperature is your average kinetic energy, energy of motion. That's going to be an intensive property. How much heat something holds in, that's going to be an extensive property. Moving along into our last set of definitions here, we have accuracy versus precision. And it's really important in every number we collect that we have some measure of accuracy and some measure of precision. Usually precision is easy to do. It's reproducible. We always say never do something once in the lab. Now we do it all the time in our classes, but that's really a time constraint issue, not a we're going to publish something issue. If you're really going to share a result of an experiment, you're going to do it more than one time. Now we could pool our class data and we'd have a reproducibility study. So that's precision. Do you do the exact, so when you say someone's precise, or they're precise in their motion or precise in their work, they're doing the exact same thing every single time. You know, they have that nice, beautiful precision. And I actually prefer precision over accuracy. You can fix accuracy issues. It's hard to fix precision, attention to detail issues. Accuracy is how close did you get to the right value, the real value, the accepted value, whatever it is. So they always use dartboards for examples here. I don't know if you can see it. It's a little hard to see in the video, but I hope you can see it. But if you have them, if the darts are clustered, and we're aiming for the red dot, if they're clustered and they're where they're supposed to be, that's both precise and accurate. If they're clustered, they're precise, but if they're away from the mark, they're inaccurate. All over the place, imprecise, not precise. But if you take the average of those dots, it's about the center, so it's really fairly accurate. And the less precision you have, to get good data, the more trials you need, statistically speaking. And then over here, we can have a large range and have the data skewed, where here we are neither precise nor are we accurate. What does that look like in more realistic? Because, you know, I'm not going to let you guys throw darts in the lab. There's a lot of good reasons for that. Okay, so here's some data. First thing we need to know is what's the real value. So let's say we're measuring 10.16 milliliter, or we're no units. Milliliters is fine. 10.16 milliliter sample. And group 1, company 1, student 1 gets this set of data in the far left column. Group 2, the middle column. Group C, the last column. So if we want to look at the accuracy and the precision, there's a couple things we can do. The simplest way, without really doing any statistics, is to look at the average value and look at the range of values. Take the highest value, the lowest value, and assume that that range is somewhat indicative of the precision of the results. Now you can always do standard deviation and variance and things like that, but let's just take a simple approach. Take the average, take the range, highest minus lowest value. So that's what we have here in blue across the bottom. So this is our average on top and our range on the bottom. If we look at that, again, first thing we need to know is what's the real value. The real value is 10.16. Clearly, column A is your most accurate data, and this value is your least accurate data. If we want to talk about precision, what's the most reproducible? This data is the most reproducible. This is the most precise data. Something's wrong. Maybe instrument's miscalibrated and they're just getting a wrong value. You can see the number's almost exactly 2 off. Maybe there's a systematic error. Those are actually easy to correct once you find them. And then our least precise also happens to be our most accurate, and that can happen as well. And that is all I have for you today. Thank you as always for your time and attention, and work your homework problems.